Okay, so you think NVIDIA makes graphics cards? Buy the chip. Sell the chip. Watch the money pile up. Simple enough, right? Except this company, a company that got its start designing processors for people who wanted smoother frame rates in video games, is now worth more than $4 trillion. More than the entire GDP of Germany. More than Apple was worth just a few years ago. CEOs of billion-dollar companies are sitting on waiting lists for 6, 12, sometimes 18 months just to get their hands on NVIDIA's products. Governments are treating these chips the way they once treated oil fields and fighter jets, as strategic national assets. So the real question is this: what exactly is NVIDIA selling that nobody else can easily replace? Because here's the thing, it isn't chips. Not really. What NVIDIA is actually selling is the future of artificial intelligence itself. And once you understand the economic engine underneath that, the $4 trillion valuations start to make a disturbing amount of sense. Let's go back to where this all started. In January 1993, 3 engineers, Jensen Huang, Chris Malachowski, and Curtis Priam, sat down at a Denny's diner in San Jose, California, and decided to build a company. Their thesis was simple but bold. General-purpose processors were going to hit a ceiling, and the future of computing would belong to specialized hardware that could handle specific complex tasks at enormous scale. The market they chose to fund that vision was 3D gaming. That choice wasn't glamorous, but it was financially logical. Gaming companies were willing to pay for better graphics. Better graphics required more and more complex calculations done faster and faster. And that commercial pressure, millions of gamers demanding higher resolution, smoother movement, more realistic lighting, created the perfect economic incubator for building what would eventually become the engine of artificial intelligence. The early years were brutal. NVIDIA's first commercial chip, released in 1995, was built on a technological bet that went wrong almost immediately. The chip rendered graphics using a technique called quadratic surface mapping. When Microsoft standardized the entire industry around a completely different approach, polygon rendering, NVIDIA's chip became commercially worthless practically overnight. The company nearly collapsed. Huang redirected every remaining dollar into a new architecture. A crucial last-minute contract with Sega kept the lights on. Then, in 1997, NVIDIA launched the Riva 128, sold over 1 million units in 4 months, and survived to fight another day. 2 years later, in August 1999, they released the GeForce 256, the first chip ever formally called a graphics processing unit, a GPU. And the trajectory of modern computing quietly, permanently changed. Here's what made that moment so significant, even though almost nobody understood it at the time. Rendering a 3-dimensional scene onto a 2-dimensional screen requires solving thousands of mathematical equations simultaneously. You have to calculate the position of every geometric surface, the behavior of every light source, the color and depth of every pixel 60 times per second. No single powerful processor working through problems one at a time can do that fast enough. So NVIDIA built chips that work differently. Instead of one extremely capable processor, they crammed thousands of smaller execution units onto a single chip and made them all work in parallel, simultaneously on different pieces of the same problem. Think about it this way. A traditional CPU is like one brilliant surgeon who can perform extraordinarily complex procedures but can only operate on one patient at a time. A GPU is like 10,000 paramedics who are each less skilled individually, but can process 10,000 patients at the exact same moment. If your goal is speed at scale, not complexity, but sheer volume, the 10,000 paramedics win every time. The video game industry spent 3 decades funding NVIDIA's research into parallel computing. And that investment accidentally created something nobody planned for. The perfect hardware for training artificial intelligence. To understand why, you need to understand the math. Deep neural networks, the foundation of modern AI, are essentially enormous systems of matrix multiplications. You take an input, multiply it by enormous tables of numbers called weights, run the result through a mathematical function, and repeat that process billions of times across millions of data points until the network learns to recognize patterns. That's it. That's what AI training actually is, underneath all the hype. And that calculation, matrix multiplication at massive scale, is precisely the calculation that GPUs were already built to perform. The same hardware that rendered light vectors onto polygons in a video game in 1999 was, structurally, the exact hardware needed to train a neural network in 2012. The coincidence didn't just change NVIDIA. It changed the entire course of computing history. But here's the thing. If it were just hardware, the story would end there. AMD can build GPUs. Intel can build accelerators. If raw silicon were the whole game, NVIDIA would just be a chip company competing on specs and price. What turned NVIDIA into an untouchable economic force had nothing to do with hardware at all. It started with a software decision in 2006. Jensen Huang made a call that Wall Street hated at the time. He committed NVIDIA to building a software platform called CUDA, Compute Unified Device Architecture. The idea was to let programmers write code that ran directly on the GPU using standard programming languages like C and C++ without having to translate everything into graphics-specific instructions first. NVIDIA dedicated transistor space on every single chip to making this work, raising manufacturing costs and power consumption while delivering zero benefit to the gamers who were still NVIDIA's primary customers. Between 2006 and 2012, NVIDIA spent over $1 billion building this ecosystem. The stock got punished repeatedly. Analysts questioned the logic. The GPU market, general-purpose computing on graphics cards, was still theoretical, still experimental. Then, in 2012, 3 researchers at the University of Toronto, Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton, entered an image recognition competition called ImageNet. They trained a deep neural network called AlexNet on 2 consumer NVIDIA graphics cards using CUDA code. Their network didn't just win the competition. It shattered the previous accuracy record so completely that the entire research community stopped what it was doing and paid attention. The error rate on recognizing images dropped from 26% to 15% in a single year. And because Krzyzewski had written his code in CUDA, every researcher who looked at that paper and thought, I need to replicate this, reached for NVIDIA hardware. Not because AMD didn't exist. Not because other options were impossible. Because the code was written in CUDA, the libraries were built for CUDA, and the tools for debugging and optimizing were CUDA tools. That moment launched the modern AI era. And it locked the entire research community into NVIDIA's ecosystem before most people in finance even knew what a GPU was. Over the years following AlexNet, NVIDIA compounded that head start by building a suite of software libraries specifically optimized for its own hardware. cuBLAS handles the accelerated linear algebra that deep learning depends on. CUDNN provides tuned routines for the forward and backward passes that neural network training requires. Essentially the core loop of every AI model ever trained. TensorRT optimizes trained models for deployment so they run as efficiently as possible during inference. NCCL coordinates communication between multiple GPUs in a cluster, making sure they can synchronize gradients without wasting cycles. None of these libraries are particularly glamorous. They're not the kind of thing that gets discussed at technology conferences in front of excited crowds. But they're the plumbing underneath every major AI system running in production today. Billions of dollars of infrastructure depend on them. And because they're tuned specifically and meticulously for NVIDIA hardware, running the same workloads on a competitor's chip, even one with comparable raw performance on paper, often means rebuilding the entire stack from scratch. This is where the economics get really interesting, and where the real competitive moat begins to show its depth. If you're a company building AI today and you want to switch away from NVIDIA, you're not just buying a different chip. You're looking at a rewrite of billions of lines of code. You're looking at retraining engineers who have spent their entire careers learning CUDA toolkits. You're looking at losing access to software libraries, cuBLAS for matrix operations, CUDNN for neural network training, TensorRT for inference optimization that have been tuned over 2 decades specifically for NVIDIA hardware. You're looking at computer science departments around the world that teach parallel programming using CUDA, which means every new graduate entering the workforce already thinks in CUDA. And you're looking at an open-source AI ecosystem where the most popular frameworks, PyTorch, TensorFlow, JAX, are integrated with CUDA at a level so deep that running them efficiently on non-NVIDIA hardware is a research project in itself. For most companies, switching away from NVIDIA would cost more in engineering time, retraining, delayed products, and operational risk than the hardware price difference could ever justify. That's not vendor loyalty. That's a switching cost so large it functions like a financial moat with walls 60 feet high. And look, if you're finding this breakdown useful, it would genuinely mean a lot if you subscribed and liked the video. It's the best way to let us know this kind of deep dive is worth making, and it helps bring this content to more people who'd find it valuable. Now, back to the economics. Understanding why NVIDIA's customers can't easily leave also explains why they buy the way they do. We're not talking about companies purchasing 10 chips or 100 chips. We're talking about OpenAI, Google, Meta, Microsoft, Amazon, the largest technology organizations in human history. Purchasing clusters of 10,000, 50,000, sometimes over 100,000 GPUs at once, the reason is physics and mathematics. Training a frontier AI model, the kind of system behind a ChatGPT or a Gemini, requires more memory than can fit on any single chip. A modern large language model might have hundreds of billions or even trillions of parameters. Those parameters have to live somewhere during training, and the memory on a single GPU maxes out well below what's needed. So the model has to be distributed across thousands of chips simultaneously, with the GPUs constantly communicating with each other, sharing data, synchronizing computations. This is called cluster training. And it means that when you buy GPUs for frontier AI, you don't buy a few, you buy a data center, because a handful of chips can't even run the software you need them to run. The scale of spending this creates is genuinely difficult to wrap your mind around. Microsoft, Google, Meta, and Amazon are collectively spending over $300 billion per year on AI infrastructure, not over a decade. Per year. That number keeps climbing because every new generation of AI models requires exponentially more compute than the last. The models are getting bigger, the datasets are getting larger, and the only way to handle that growth is to buy more chips. Which brings us to pricing power and to the economic mystery at the heart of NVIDIA's financial story. A single NVIDIA H100 GPU, the previous flagship accelerator, commands between $30,000 and $40,000 on the market. The raw cost of manufacturing that chip, including all the components and assembly, sits somewhere under $4,000. That's a markup that would make a luxury watchmaker blush, and yet customers pay it, willingly. Sometimes desperately. In fiscal year 2026, NVIDIA reported total revenue of nearly $216 billion, with data center revenue alone hitting nearly $194 billion. The gross margin, meaning the percentage of revenue left over after subtracting the direct cost of making the product, sat between 71 and 75%. To put that in context, traditional hardware companies like Dell or HP operate with gross margins somewhere between 15 and 25%. Pure software companies like Microsoft or Adobe achieve margins in the 70 to 85% range because reproducing a software license costs almost nothing. NVIDIA is achieving software company margins while producing physical hardware. That almost never happens. And it happens because of pricing power. The ability to charge almost whatever you want, because demand vastly exceeds supply, and customers have no viable alternative. Here's where the pricing power connects to a supply chain that most people have never thought about. NVIDIA itself manufactures almost nothing. It doesn't own a single chip fabrication plant. The entire physical production of NVIDIA's most advanced chips, the Hopper architecture, the Blackwell architecture, the Rubin systems coming next, runs through one company in Taiwan called TSMC. Taiwan Semiconductor Manufacturing Company controls over 90% of the world's advanced semiconductor manufacturing, and NVIDIA is one of its most critical customers. Building a modern chip fabrication facility costs over $20 billion in capital expenditure and takes years to construct. Rather than carrying those costs on its balance sheet, NVIDIA chose the fabless model. Design the chip in California, outsource the actual manufacturing to TSMC, and keep its own capital free for software, engineering, and research. This lets NVIDIA spend $23 billion a year on research and development without being weighed down by the economics of running factories. But it also creates a dependency, and that dependency points to the single biggest physical bottleneck in the entire global GPU supply chain. NVIDIA's chips are extraordinarily complex to assemble. They don't just print silicon. They use a technology called CoWoS, chip on wafer on substrate, which allows NVIDIA to stack the main compute die directly alongside multiple high bandwidth memory chips on an ultra-dense silicon interposer that enables data transfer speeds exceeding multiple terabytes per second between the processor and its memory. This is what allows these chips to handle the enormous memory demands of AI training. The problem is that CoWoS packaging requires ultra-precise manufacturing tolerances and highly specialized equipment. TSMC has limited production capacity for it. Expanding that capacity takes years. And because global demand for NVIDIA's chips dramatically outpaces what TSMC can physically produce, waiting lists of 6 to 18 months are not marketing fiction. They're the mathematical consequence of trying to satisfy global AI demand through a single-point supply chain with a physically constrained manufacturing process. That scarcity is also, paradoxically, one of the things sustaining NVIDIA's pricing power. When demand exceeds supply by a significant margin, customers can't bargain on price. They compete on who can secure delivery at all. What most casual observers miss when they look at NVIDIA's financials is that the GPU itself, as extraordinary as it is, represents only part of the business. In 2020, NVIDIA made an acquisition that most market commentators underestimated at the time. They paid $9 billion in cash for a company called Mellanox Technologies, an Israeli firm specializing in high-performance networking hardware. At the time, Mellanox was generating about $1.3 billion in annual revenue. The price looked steep. Jensen Huang understood something the skeptics didn't. When you connect tens of thousands of GPUs in a training cluster, the GPU computation is only as fast as the network connecting them. If the communication between chips is slow, if one GPU has to wait even milliseconds for gradient updates from another, the entire cluster stalls. You've paid for 100,000 of the world's fastest chips, and they're sitting idle waiting for data to move. The network fabric is not a secondary component. In large-scale AI training, it is frequently the primary bottleneck. By integrating Mellanox's high-speed networking technology, InfiniBand for supercomputing environments, Spectrum-X Ethernet for enterprise cloud environments, NVIDIA transformed from a chip company into a complete data center platform company. NVLink and NVSwitch interconnects now deliver high-bandwidth unified memory channels across every GPU in a server chassis, allowing thousands of chips to behave more like a single unified processor than a collection of individual components. By fiscal year 2026, NVIDIA's networking division alone was run at an annualized revenue rate exceeding $31 billion. Their networking revenue in a single quarter surpassed what legacy networking giant Cisco generates across its entire enterprise business. A company that bought a networking business for $6.9 billion was, within 5 years, operating the largest networking infrastructure business in the AI data center market, and the strategic logic goes beyond revenue. By building the networking layer into its own platform, NVIDIA made it structurally harder for customers to adopt a competitor's GPU. You can't simply swap NVIDIA chips into a data center where everything else, the switches, the interconnects, the communication libraries, is built around NVLink and Spectrum-X protocols. Replacing the GPU means replacing the network. Replacing the network means rebuilding the data center. The switching cost compounds with every additional NVIDIA product a customer adopts, and this scarcity has turned GPU allocation into something far beyond a commercial negotiation. It has become geopolitics. The United States government, recognizing that advanced AI capabilities translate directly into military and intelligence advantages, implemented strict export controls on NVIDIA's most powerful chips. The H100, the B200, and their regional variants are now restricted from export to China and other designated markets. China historically represented 15 to 20% of NVIDIA's data center revenue. Losing that access in a single regulatory action reshaped global trade flows and forced Chinese technology companies to accelerate domestic alternatives, primarily Huawei's Ascend chip series. Meanwhile, governments in Europe, the Middle East, and Southeast Asia are spending billions in state funds to build national AI computing reserves. They are buying NVIDIA supercomputers, constructing sovereign data centers, and training AI models adapted to their own languages and regulatory frameworks. Countries like Saudi Arabia and the UAE are making GPU procurement a diplomatic priority. NVIDIA's sovereign AI business grew over 80% year over year during this period. The company is now operating in nearly 40 countries through state-funded programs. GPU allocation has become a tool of international diplomacy. Which nations secure early access to advanced compute hardware and which ones don't is shaping which countries will build domestic AI ecosystems and which will remain dependent on foreign cloud infrastructure for decades. NVIDIA isn't just selling technology anymore. It's influencing the architecture of global power. Now, at this point in the story, most financial analyses would pivot to discussing competitors. AMD and Intel are both developing accelerators. Google has built its own custom chips called TPUs. Amazon has Trainium. Microsoft built Maya 100. Surely one of these alternatives is going to break through? The reason that analysis consistently underestimates the problem is that hardware is only layer 1 of a 6-layer challenge. To displace NVIDIA, a competitor needs to win on transistor performance, high-bandwidth memory integration, GPU to GPU interconnect speed, optimized compilers and math libraries, native integration with AI development frameworks, and, perhaps hardest of all, 2 decades of developer trust and institutional familiarity. Win on 5 of the 6 and lose on 1. And enterprise customers still don't switch, because switching on a half-finished ecosystem introduces risk they can't afford. NVIDIA is also not sitting still. They moved from the Hopper architecture to Blackwell, and they're already developing Vera Rubin. Every generation delivers multi-fold performance improvements, meaning competitors aren't chasing a fixed target. They're chasing a moving one that is accelerating, and the competitive advantages don't stand alone. They reinforce each other. High gross margins generate the cash flow that funds the $23 billion annual R&D budget. That R&D budget drives the roadmap acceleration. The roadmap acceleration attracts more developers to CUDA. More developers on CUDA deepen the switching costs. Deeper switching costs sustain pricing power, and pricing power sustains the gross margins that fund the R&D. It's a flywheel. And NVIDIA has been spinning it for 15 years. But the story would be dishonest if it stopped at the advantages. NVIDIA's data center revenue is heavily concentrated. Roughly half of it comes from just 4 hyperscale cloud providers: Microsoft, Google, Meta, and Amazon. If those companies simultaneously reduce their AI infrastructure spending, or if they successfully develop in-house custom chips that reduce their dependence on NVIDIA, the revenue impact would be immediate and severe. And crucially, those 4 companies have every financial incentive to reduce that dependence. Each of them is spending tens of billions of dollars per year on NVIDIA hardware. Even a 20% reduction in that dependency, achieved through in-house silicon, translates into hundreds of billions in savings over a decade. Google's TPU program, Amazon's Trainium, and Microsoft's Maya are not hobby projects. They are existential strategic investments. Even if they're unlikely to eliminate NVIDIA's advantage entirely, the geopolitical risk is not hypothetical. NVIDIA's most advanced chips are manufactured almost entirely on the western coast of Taiwan. The geopolitical tension in that region is real and ongoing. A disruption to TSMC's operations would not just damage NVIDIA, it would be a global economic catastrophe. But NVIDIA specifically has no backup foundry capable of producing advanced packaged silicon at comparable scale. There is also the question of whether the AI investment cycle has gotten ahead of the revenue it needs to justify itself. Sequoia Capital published an analysis pointing out a significant gap. If you take NVIDIA's annualized revenue, multiply by 2 to account for total data center operating costs, then multiply by 2 again to reflect the profit margin end users need to generate from that infrastructure. The global AI ecosystem needs to produce roughly $600 billion in annual end-user software revenue to justify current hardware spending. Actual realized AI software revenue across all consumer and enterprise applications is closer to $100 billion. That's a $500 billion gap. It doesn't mean the AI build-out is wrong. Early infrastructure always runs ahead of the applications it enables. The internet build-out of the late 90s looked wasteful until it didn't. But it does mean that there is a real possibility of a digestion phase, a period where cloud companies pause procurement while the software applications catch up with the hardware. If that happens, NVIDIA's revenue growth slows, its valuation multiples compress, and competitors get the breathing room they need. These are not small risks. They're the kinds of structural vulnerabilities that even dominant companies can't fully engineer away. What separates NVIDIA from every other chip company, though, is that it recognized early what business it was actually in. Traditional semiconductor vendors design hardware to meet generic standards, sell it to system builders, and rely on external communities to build the software. They compete on price and performance specifications. That's a commodity business, and commodity businesses have thin margins and brutal cycles. NVIDIA is not